Okay, so yesterday we talked about an introduction to energy. First, bioenergetics, which was just a definition of how living things use energy. Because we went through the formula for energy and energy transformations. However, I told you that our application of it will not be the same as how you would apply it in chemistry or physics, because we're focusing on how living things use energy. So I said that we are open systems, and I actually have a diagram I'll show you of this today that I think clarifies it. In a closed system, if we just mix stuff together and that's it and let it go, the reaction will come to an end, or it'll reach equilibrium. If we reach equilibrium, we wouldn't be alive. We are constantly taking in food, taking in oxygen, utilizing those reactants and making products. Our energy source, we said, was the sun, and the sun got to us from the plants, from photosynthesis, and then the consumers would get the energy from there. Metabolism, we said, was the sum of all of our reactions, and it was made up of two things: anabolism, which was the building up of stuff, and catabolism, which was the breaking down of stuff. If you do more building than breaking down, you would gain weight. If you do more breaking down than building, then you would lose weight. All right, and then we classified each of these. Digestion was which? Anabolism or catabolism? Catabolism. We said photosynthesis. Anabolism, building stuff. How about cell respiration? Catabolism, breaking down sugar into something simpler, and then anything with synthesis after it would have to be what? Right, anabolic, anabolism, so we're building something. And then I explained, and we'll talk about this in a lot more detail in the next two chapters, that most of the reactions that happen in our bodies are not one-step reactions. And so we call it a metabolic pathway when we have a series of reactions to get from a particular starting point to a product. And an excellent example of this that you'll see in the next couple chapters would be cell respiration. We start with sugar, glucose, but then glucose goes through like 8 steps and becomes pyruvate, and then pyruvate goes to the citric acid cycle or Krebs cycle. And there's this series of multiple steps to release the energy from glucose, not in one giant step. Same way gasoline runs your car. You're releasing the energy from the gasoline in several steps so that then you can convert it to mechanical energy to run your car, as opposed to just lighting it on fire and releasing all the energy from the gasoline at one time. Okay, we talked about energy. We talked about two types of energy, potential and kinetic. But I told you that our focus would be what specific type of potential energy? Chemical energy, right. The energy that was stored in bonds. We have kinetic, which is the energy of motion, potential, which is stored energy, and then chemical energy, which was specifically what's stored in bonds, as opposed to learning about positional energy, because you're at the top of a hill and then you roll the rock down the hill, and that's kinetic energy, and now it has a lower state of energy. We won't be discussing that in those terms. All right, then we got to the laws of thermodynamics. The first law of thermodynamics is that energy can't be what? Created or destroyed, but it can do what? Transform. It can transform. It can go to different forms. So the amount of the universe is constant, and that it can't be created or destroyed. It's the law of conservation of energy. You learned it in chemistry. You probably learned it in physical science. And I even had a diagram. And the thing is, when you think about it, you say, but I don't understand. I mean, if I run a marathon, don't I lose the energy? I burned off the energy. But the thing is, you don't actually lose the energy. It just gets transformed into a different form. Oh, okay. Well, that's all right. I'll let this go. Okay. And then we said that the second law of thermodynamics was that during each transformation, some of that energy gets converted to forms that are no longer usable. And we said that some of it got converted to heat, and then I gave you this example of the bananas. You eat the bananas. Some of the energy then gets converted to mechanical energy, some of the energy heat, and I think I showed you this, correct? All right, and that free energy, we're going to call free energy the energy that's useful to us. All right, then we talked about entropy, and I actually added a new diagram here that I think illustrates entropy a little bit better. I told you that entropy refers to disorder or randomness. And notice the guy throwing the bricks. If he's throwing the bricks up in the air, remember, spontaneous has to do with the direction a reaction will normally go. So if he's throwing the bricks up in the air, the spontaneous way the bricks would probably land would be on the right. They would probably land in a disorderly stack. In order for him to throw the bricks and have them land in this perfect stack, that would be very unlikely. In fact, that would probably not be spontaneous. He would have to have a constant input of energy to organize the bricks like that. So I thought this was a better illustration than what I had up yesterday of entropy. So entropy was the measure of randomness, and spontaneous reactions tend to go towards increasing entropy, things being more simple, more stable, just randomly moving around. And then I told you that every time energy is transformed, entropy tends to increase, everything tends to move towards equilibrium. Gasoline, octane, C8H18, very complex. Think of a molecule of gasoline as very, very orderly. If I break that gasoline down, now I've got a whole bunch of CO2s and H2Os, it reacts with oxygen, and that's much less orderly. Now I have a bunch of little molecules randomly bouncing around as opposed to one very organized molecule. All right, so entropy tends to increase. And then we got to this formula, correct? Yeah. Okay, so free energy, we said, was the energy that's available to do work in our cells, and that the change in free energy is related to the total energy that something has minus the change in entropy. And then temperature had an effect on this. And then did we go through, I know I told you this, and this, and then this, right? Spontaneous and not spontaneous. Yeah. And then did we do these practice ones? Mm-hmm. All right, perfect. So just to do a quick reminder of these practice ones, if I can find my little writing utensil.
It's on the other side of the board.
Thank you.
You're welcome.
Okay, so we said that anything that, and this makes perfect sense, if the total energy that something has increases, so that means now I have more energy than I started with, and delta S is negative, so now we're talking about less entropy, something becoming more organized than it was, then delta G would tend to always be positive, which makes sense. I'm gaining energy and I'm making something more disordered. I'm putting those bricks in a pile. The opposite of that, I told you, if delta S is positive, so now we're talking about entropy increasing. Now it's becoming more disordered, and the delta H is a negative number, meaning now we have less energy than we started with. That means energy is going to tend to be released, and so delta G would tend to be a negative number. However, if both of them are positive, we can't really decide.
It depends on the temperature.
Right, and I told you that the factor that would then possibly determine it might be the temperature. Yes?
Why don't they all depend on the temperature? How would you know?
Well, but in this case, look, if delta S is a negative number, then that would mean a negative minus a negative would make this positive. And if delta H is also positive, we now have a positive plus a positive. There's no way delta G can be negative, no matter what the temperature is, because it's in Kelvin. Yeah. And then the same is true the other way around. If we go this direction and delta H is a negative number and this is a positive number, you now have a negative plus another negative. It doesn't matter what the temperature is, delta G is going to have to be negative. So that's why temperature has an effect only in that one situation. And so the higher the temperature, that would tend to make some reactions happen that possibly wouldn't go on their own. Okay, so endergonic versus exergonic. I think this is where we need to start. Okay, so an endergonic reaction and an exergonic reaction, we're using the term exergonic, exo, out, and gonic referring to energy. So an exergonic reaction is any reaction that releases energy. It's basically the name for a reaction with a negative delta G. Exergonic. And endergonic is the opposite. Any reaction that picks up energy, that requires energy, is going to be a positive delta G, and that's not going to be spontaneous. So endergonic and exergonic. And then I have a diagram to show this. Now remember, G itself, I know the kids are going to come in now. Oh, we got 2 words. Yay. That's all right. I have a better recording of the first part. All right. Here's a diagram. Just to clarify before they come in here, this is G. G itself cannot be a negative number. It has an amount of energy, or it could have no energy, but it can't have a negative amount of energy. What can be negative is delta G. Here's the reactants. Here's the products. Delta G is negative because energy, in this case, was released. So this would be an exergonic spontaneous reaction. Here, delta G is positive. Reactants, products, and energy had to be put in to do this. This could be like photosynthesis. Where does the energy come from for photosynthesis?
No, that's
From the sun. So this could be photosynthesis. This could be cell respiration, and the energy ends up getting captured by ATP. So energy being released. In chemistry, sometimes you learn endothermic and exothermic. But therm has to do with what? Right, heat energy. And we're talking in general about energy, so that's why we use endergonic and exergonic instead. All right, again, in a closed system, you eventually reach equilibrium where delta G is 0. Living cells are not closed systems. We're constantly taking in energy, using up the products, so that G never reaches 0. There are always chemical reactions going on unless the cell dies. Then it reaches equilibrium. And let me show you a diagram of this, and then I'll go back to this slide if you still need it. So don't worry if you didn't get that. I'll go back because I know the kids are going to come in. Here's an example of a closed system. So here we have an exergonic reaction. This would be our energy being produced, and the energy is being used to light the light bulb. And this would be a negative delta G. But this is a closed system. So eventually it reaches equilibrium. No more work is being done. Now, here is an open system. Constant energy input. Oops. Constant, now here is our spinning thingy. And that's the official word for that, a thingy. And here's our light bulb being lit. And in our case, I told you that a lot of times what we have is a metabolic pathway. So this would be like cell respiration. Here's the breakdown of glucose starting here. We break it down a little, and we have our final products at the end. And ATP would actually be like this. This would be ATP. And this would be the reaction that needs the energy. So now the reaction that needs the energy gets it. ATP just carries the energy from here to there. All right, I know they're going to come in, so I'm going to go back to this slide and let you finish it. And then tomorrow we'll pick up from there, and I'm going to give you the remainder of the period to work on your